Welcome back to a video series on MAC 1105 College Algebra. My name is Sean Perry. These are guided notes number 22 in the series on Chapter 5.1, Exponential Functions. In this section, we want to continue our investigation of the exponent, which we began when we started to investigate polynomials. However, in a polynomial term, the constant is the exponent itself, with the caveat that the exponent must be a positive whole number. We eventually extended this idea to rational functions where we could have a negative whole number, and radicals, where we were even allowed to have fractions in the exponent. But all of these still put a constant value into the exponent and left the variable in the base. The exponential is going to switch things around. Now our base is going to be a constant, which is going to need to be a positive number in order to keep things from becoming complex valued when we take a fractional exponent here. And we're going to want it to be the case that b is not equal to 1, or else we just get 1 to some power, which is the constant function 1 and doesn't really have the same behavior as the other exponentials. So keeping our base positive keeps us from having complex values where something like a 1/2 would be up here in the exponent, because that would be complex. And excluding 1 just keeps us from talking about the constant function 1 when we talk about an exponential function. We're going to see two kinds of bases. We're going to see bases which are between 1 and 0, and bases which are greater than 1. Bases which are greater than 1 will have a certain morphology. They will have a tail that hugs the asymptote at y equals 0 as you go to the left, and as you go to the right, they will grow without bound. Anything to the 0th power is 1, so they'll all pass through 1, 0, and anything to the first power is just itself, so they will all pass through 1b. Now that's also true with the fractional bases, but they are going to be reversed compared to their larger than 1 based counterparts. They still go through 0, 1, and in fact, they still go through 1b. It's just that b is now some value between 0 and 1. We can see, though, that their tail is now pointing in the other direction. It gets smaller as time goes on, and so this is called exponential decay. On the other hand, this one gets larger as we go to the right, so this one is called exponential growth. We will see examples of both of these shortly. To start with, let's just talk about evaluating a function 4 to the w. What we want to do is plug whatever is in the function argument slot here into the exponent. 4 to the 0 is just 1, 4 to the minus 1 is 1 over 4, 4 to the 5th is the same as 2 to the 10th, which is 10/24, and 4 to the 1 is just itself, that's 4. So to evaluate these, it really isn't any different than plugging in whatever the argument of your function is into the exponent slot and evaluating that. Keep in mind that evaluating these whole numbers is no different than multiplying 4 by itself 5 times. And we keep in mind that anything to the 0th power is always 1, and anything to the negative 1 power is 1 over that thing, or its reciprocal. For number 2, we have an example of a base which is between 0 and 1. That is to say, it's a proper fraction. But we still evaluate it the same way. I just replace y with 1, something to the first power is itself. Replace y with -3, and here I'd like to evaluate the negative part first. That's going to take 1 over 2/3, or 3/2, its reciprocal. And then raising each of these to the third power, I get 3 to the third, which is 27, over 2 to the third, which is 8. Here, I'm doing the same thing. I'm taking and replacing the y with a 2, like this, which is what we're directed to do here by having a 2 in the parentheses. And then I want to square both the top and the bottom to get 4/9. Here I'm plugging a 0 into the exponent, and anything to the 0th power is 1. I should provide the caveat, of course, not everything. We should keep in mind that 0 to the 0th power is actually undefined. I could talk more about why that is in a separate video, but for right now, let's just take it as something similar is going on to dividing by 0. We cannot allow this collection of symbols to have any mathematical meaning, or else there are untoward consequences. Here we're asked to evaluate something that has an e in it. Without getting too distracted, I'll just say that e is somewhat like pi in that it's a number, first of all, and it is an irrational number, one whose decimal goes on forever without developing a repeating pattern. E shows up in a lot of different places, just like pi, when we find ourselves doing mathematics. And as far as where it comes from, for now, I'll just say that it comes historically from a bit of financial mathematics, where we were wondering about the behavior of this sequence. If I add a little something to 1, but then raise that to a proportionally large power, what happens? Well, it turns out as n goes to infinity, this doesn't go off to infinity, it doesn't shrink down to 1. What it does instead is curious. It actually turns into this constant e as n gets larger and larger. You can try this out for yourself by plugging in some very large values of n, and you can watch this pattern stabilize. Now, we'll talk more about E in just a bit, and a lot more about it in future classes. But for right now, let's just take it for what it's worth. It's a number, and we can evaluate it out to a certain degree of decimal accuracy by plugging it into the calculator. When we don't need to plug something into the calculator are situations like this, where I know e to the 0 is just 1, and so this can be exactly evaluated as a 4. On the other hand here, if I plug in 0, subtracting 1, I'm going to have a 4 times e to the minus 1, or 4 divided by e if you like. On all scientific calculators and above, there should be an e to the power of something button. If we wanted to put e to the first power here, we could get the value of e. But we want 4 times e to the minus 1 power for now, which we can evaluate as follows. Here, for reference, is e to the first power. Now, if I wanted 4 times e to the second power, I could do that just as easily. So let's just continue from there. Rounding to the appropriate decimal places, we get the following as our answers. Now, I couldn't help but notice f of 1 is repeated in 2 places here. Perhaps they meant f of minus 1. Or they just chose these at random and forgot to rule out, picking things twice. So in any case, we would wind up with, in this example I've created, 4 times e to the minus 1, or minus 2, and that gives us 4 over e squared, which is something like 0.5413. The next question asks us to match certain graphs with certain equations, and we're going to want to take advantage of our transformation of function rules to make that happen. The first thing we should do is find a good parent graph. Here we have 4 to the power of x, which we know has a horizontal asymptote at y equals 0 out to the left, and goes through 0, 1, and goes through 1, 4. So we can compare this graph to the other graphs above and cross-reference that with these particular manipulations of that parent graph. So what's the difference between f and e? Well, there's a minus sign next to the x. This is inside the function, and so is a horizontal type transformation, and the negative sign makes this a reflection. So horizontal reflection is what we're going to get, or reflection over the y-axis. For this one, the negative sign is multiplied on the outside, and so this will be vertical reflection, or reflection over the x-axis. For C, we have both. So we want to reflect once and then reflect again. This one is subtracting by 3, not multiplying by a negative, but adding a negative or subtracting. And that is going to be a right shift by 3. It's horizontal because it's inside of the function, and horizontal shifting goes against its sign. On the other hand, this negative 3 is outside the function. Notice how close these are to one another, and really it's only the size of the font for the minus 3 that tells you that this is outside of the exponent and not upstairs with it. So outside is going to be a vertical transformation. This is a downshift by 3. So let's take a step back and compare each of these graphs. So for our parent function, that's going to look like this. Notice going through 0, 1, and 1, 4, and having our tail to the left at y equals 0. Now, what about this downshift by 3? So downshifting is going to downshift the horizontal asymptote as well. And so we should look for one that has a horizontal asymptote at minus 3. There it is. This one is a right shift by 3 that won't change the horizontal asymptote, but it will shift the point 0, 1 over to 3, 1. And we can see this graph goes through 3, 1. This has been right shifted over compared to this one. The next one, horizontal and vertical reflection, Well, bringing this down and then reflecting it over, we're going to have a tail that goes to the left, and exponential sort of curve is going to be down in the lower left quadrant. That's going to be this one right here. So that's C. D is vertical reflection. That's just taking the parent and reflecting it over the x-axis. So that's this one here. Horizontal reflection, same thing, but over the y-axis. So that's going to be this one here. And that's going to do it for this problem. The next one is also a function transformation matching problem, but they've changed our base to be something between 0 and 1. Notice we have a 1/3 here. So that's going to look like exponential decay. Our tail is going to be over here on the right. And we should note that at -1, 1/3 to the -1 is 1/1/3, or 3. Now that's going to give us another point that we can kind of identify, -1, 3. And we can use that to match this parent. But let's take a look at the transformations. We have a horizontal reflection, composition with a times -1. We have times -1 on the outside, that's vertical reflection. We have -3 on the outside, a downshift by 3. We have -3 inside the function, that's a right shift by 3. And finally, we have two negative signs here multiplying by our function on the inside and out. That's horizontal and vertical reflection. So let's see if we can find those things on our graphs. So first of all, here's our parent, right? It goes through 0, 1, and it goes through -1, 3. You can even kind of see how it goes through 1, 1/3. So our tail is off to this way, still at y = 0, but now a right-pointed asymptote for our horizontal asymptote. And let's do this other one. So how about horizontal reflection? So that's over the y-axis. Here we are here. Vertical reflection would be over the x-axis here. Downshifting by 3 will change our horizontal asymptote. It's going to move everything down, including that horizontal asymptote. So here we are. And right shifting is going to take these values and move them over to the right by 3 units. It's easy to see how that goes for 0, 1. It goes to 3, 1. So that's here. Okay, this next one asks us to identify the transformations and graph this function g of x is equal to 3 to the x minus 1 minus 4. Now, these two transformations correspond to a right shift by 1 and a downshift by 4, respectively. And we're going to apply those to the parent function 3 to the x, which looks like this. For this one, I graphed the parent function so that we can kind of see what's going on, including a couple points that are on that parent function. And here you can see they have each one of them gone down 4 and over 1 to the right. That includes the horizontal asymptote, which was at y = 0 and is now down at y = -4. But since we are just translating this, it still is a horizontal asymptote going off to the right, going off to the left, and nothing else has really changed, including the shape of this thing. That is to say, we do not anticipate these two curves would intersect anywhere. Now, what about domain and range? You might have noticed that there's really no values we cannot plug in to an exponential. Exponentials, like polynomials, will have the entire real number line as their domain because there's no value I can't put into the exponent here. However, our range is cut off by our horizontal asymptote. It doesn't get lower than that. And so that forms a lower bound on our range. The equation of this horizontal asymptote is the horizontal line y = -4. Likewise with this one, we have g of x is equal to 2 to the minus x minus 2. We want to identify our transformations. One is due to this minus sign here, and that's horizontal reflection. The other is due to this -2 here, and that is a downshift by 2. So we want to do those two transformations on a parent function that looks like 2 to the x, which has a horizontal asymptote at y = 0, a leftward pointing tail, it goes through 0, 1, and it goes through 1, 2. So let's think about all that. We want to reflect it and then downshift it. So reflecting it is going to take us from, let's say, 1, 2 over to -1, 2, and then we want to downshift that by 2. So that would bring our point here over to here. That would bring our point at 0, 1. Well, reflecting doesn't move that, but downshifting it brings it down here. And we also have our horizontal asymptote downshifted, and that horizontal reflection changed what direction the tail was pointing in. First, it was pointed to the left, now it's pointed to the right. This doesn't change the domain at all, and the range is just downshifted by 2, so we have a lower bound at -2. The equation of the horizontal asymptote is also downshifted from y equals 0 to y equals minus 2. Here we have one where they've asked us to graph these two very closely related functions on the same set of axes. The reason that is closely related can be seen by considering the horizontal reflection of the graph of 5 to the x. This is the same thing as 5 to the minus 1 to the x, because minus x is just minus 1 times x, and power to a power is the product of powers. But this tells me this is 1/5 to the x. So consider that the graph of 5 to the x and the graph of 1/5 to the x are going to be horizontal reflections of each other. And that's what we can see on this graph here. That is, in fact, the symmetry they want us to note, is that the two are reflections of each other. And that is because of this property here. For the next dozen or so questions, we're going to want to exploit a very, very important property of exponentials, and that's that they're one-to-one. One-to-one functions pass the horizontal line test. That means that whatever they do, they really don't repeat themselves in the same way that like a parabola repeats y values. There might be two different x values that made a certain y value pop up. With one-to-one functions, that's not the case. Every time you have a given y value, there's only going to be a single x value that does that. And so what you know is if the two outputs of a one-to-one function are equivalent, then their inputs must be the same as well. And that's true even if we are talking about functions in the argument. So for especially things like the exponential function, we should keep in mind that if we can get the bases to be the same, we can set the exponents to be the same as well. And that's because of this injectivity one-to-one property here. So how does that apply? Well, if I know something like 10 to the x is equal to 10,000, both of these can be rewritten as powers of 10. 10,000 is 10 to the fourth power. And that means that their exponents must be equal, so x must be equal to a 4. With this next one, they're not the same base yet, but they're both powers of 3. If I write 81 as 3 to the fourth, and I write 27 as 3 to the third, then I have that 3 to the 4x must be equal to 3 to the third, because the 3 to the 4 to the power of x is 3 to the power of 4 times x. Power to a power is the product of powers. And so then we can equate the exponents and get 4x is equal to 3, and solving, get x is equal to 3/4. Now, both of these started with the exponential term alone. This one has a mix of multiplication and subtraction and an exponential term. We want to begin by isolating the exponential term. That is to say, getting rid of everything else with inverse operations. I get rid of my minus 26 by adding 26 to both sides. I get rid of my timesing by 2 by dividing by 2 on both sides. And then I just have an isolated exponential. 5 to the power of n is 625. Well, as it would have it, 625 is 5 to the fourth power. And so n must be equal to 4. For this next one, we just have a little bit of work to do to isolate the exponential. Adding 22 to both sides, we get 32 is 2 to the x. 32 is 2 to the fifth, and so x must be equal to 5. Same trick here. We want to isolate the exponential by adding 7 over to this other side to get 125 is equal to 5x. Now, 125 is 5 to the third, and so x must be equal to 3. 17 is kind of a funny one because we have a negative power of 2 here. That's no big deal. 1/2 is 2 to the minus 1, and 256 is 2 to the 8th. So once we have things written that way, we can equate the exponents to say that negative x is equal to 8, and therefore x is equal to negative 8. 18 has a similar trick. We want to rewrite 1/10,000th as 10 to the minus 4, and 1,000 as 10 to the third. Then we have that 10 to the 3x must be equal to 10 to the minus 4, and so 3x must be equal to minus 4. That gives us a value of x is equal to 4/3. 19, we already have like bases, and so all we need to do is equate the exponents. From there, it's a quick process of moving our x's to one side and our numbers to the other to get that x is equal to minus 1. For number 20, we want to equate these, but their bases aren't the same, so we need to rewrite it. 49 is 7 squared, and it turns out 343 is 7 to the third. This gives us that 3 times x plus 5 is equal to 2 times x plus 5. Now, distributing the 3, distributing the 2, and then grouping some like terms, we find that x must be equal to minus 5. The same trick is used for 21. 27 is 3 to the third, and 180 over 81 is 3 to the minus 4. We want to bring those powers into the exponents and distribute them, and then set those two exponents equal to each other. Solving gives us 26 over 7. For number 22, we have something in terms of z's, but since the bases are the same, we can just start by equating the exponents. That gives us a polynomial to solve, which we do by bringing things over to one side, setting it equal to 0, and factoring. This gives me a z equal to -4 or +1. Number 23 is similar. We have a polynomial in the exponent. We want to get our bases the same, so we rewrite 32 as a power of 2. And this lets us equate the exponents once we have like bases. Regrouping and factoring, we find the following two roots. Finally, here we have something in terms of a base of 4. This is actually 4 to the -3. And so rewriting that, we can equate our exponents, group them all on one side, set it equal to 0, factor, and solve for x. For number 25 and several problems after, we're going to look at the compound interest formula. Compound interest is basically looking at the amount of money you have, including previously accrued interest, to determine future interest. The way that we do this is by selecting a number of times per time unit, usually a year, to give you a fraction of your interest percentage. But then we're going to want to reassess how much interest should be in there an equal number of times per year. So the main goal here is going to be to figure out what is P, R, N, and T for each problem and plug them into this equation. A key issue is they want you to assume there are 365 days in a year, excluding leap years. You'll also see this as the banker's 360 days in a year for sort of making the math a little bit easier to do. You'll see that in some problems as well. So this one says if $13,500 is invested for 27 years and earns 9% interest compounded daily, then how much do you get at the end of that time? So here you want to identify P, T, R, we're going to need the decimal version of this percent here, and N, compounded daily, is 365. We plug that all into the calculator. You're going to want to be careful to use enough parentheses to make sure everything is in the right place and is going in the right order. When you press to the power of, some calculators will put you into the exponent, where we can clearly see that we are exponentiating by a product. If they don't put this into the exponent, I strongly encourage you to put this part in parentheses after your caret. So I'm not going to type each one of these into the calculator. I'll just remark that when you are semi-annually compounding, you are looking at an n value of 2. When you are compounding quarterly, they mean you're doing it 4 times a year. And when you're doing it annually, it just means you're doing it once per year. 26 is a nice problem because it doesn't change anything except for the compound scheduling. That is to say, are you compounding annually, semi-annually, etc.? And what we're going to notice is that we have a really big increase of about $20,000 between compounding once a year or twice a year. However, the amount goes down to only about $11,000 more when we double it again. And when I multiply that by 3, I only go up by $8,000. So we see that we're still getting more money the more that we compound, but it's sort of a diminishing return. We get less money at each jump in the compounding schedule. And that's on display here when we go from 12 times a year to 365 times a year. Notice that we only gained about $3,000 more versus the $20,000 that we had from the first jump. Now, I thought this would be a good time to mention that if you let n go to infinity, that's where e comes from, and we get this new formula for our amount after a given time. If we were to compound every instant of every day, what we call continuous compounding, that would still only go up by, in this case, about $100. So still increasing, but diminishing returns as we increase our compounding schedule. So here we have a problem diving into that. It's another kind of evaluation problem. So I'll just make one quick note of how that would look plugged into the calculator, right? We would identify our P, our T, and our R. If we are continuously compounding, then that's going to have the form P times E, which is right here, to the power of 5.5%, keep track of your decimals there, times 22 years, as such. Round to the nearest cent, as is appropriate for dollars. And let's just note this should be 33,000, but the rest of the answers will be as such. For 28, we have a problem about inflation. So inflation is going to be calculated from the current value of something. The future value will be 1 plus the rate of inflation to the power of t. Notice how similar this is to annually compounded interest. So we identify the initial value of something, the inflation rate, 0.011, and the amount of time. Plugging those into this formula, we get the future value of, in this case, a single-family home. But this also applies to any other goods or services like healthcare. If something costs $9,345 today and it's inflating at a rate of 5.2% per year, then after 38 years, plugging it all into the formula as such, that same procedure will cost $64,000. Another thing that we can use exponential equations to model is population growth. I should note that usually these models break down over time and they don't stay exactly with these particular rates and numbers. Lots of things change the rate of immigration and emigration from a region. But here you can see that the 190,000 term is our principal amount. This looks a lot like continuously compounded interest, but with a rate of 0.014 and an initial amount of 190,362. And they're asking for what will the new population be in a certain number of years? Well, we just need to replace the values of t appropriately. Notice that if we replace the value of t with a 0, this would be either the 0 or 1, and we would just get the initial value back. Here, plugging in a 1, we get 193,000, and so on and so forth to get the values of population later in a certain number of years. Alrighty, that's going to do it for this video. Thank you very much for your patience, and have a great day. Good luck with your studies. I'll see you in the next one.